Hello, Chemistry 30, and welcome to your lesson on standard cells and voltages. So today's objective is explain the values of standard reduction potential are all relative to 0 volts as set for the hydrogen electrode at standard conditions. So first of all, we're going to begin by talking about this hydrogen half cell on your redox table. You'll notice that this is actually the 0.00 volts value. Now, that being chosen as 0 was essentially an arbitrary decision. That doesn't mean that it has 0 voltage. And in fact, voltage is always a comparison between like 2 points of a circuit. So when I'm talking about a cell, it's a comparison between the two half cells and essentially their pull for electrons. So when I choose 0, that 0 is essentially meaningless. It's just kind of like what I call 0. It's arbitrary. In the same way that if I have 0 degrees Celsius, right, that doesn't matter in terms of a temperature change, right? If I went up 10 degrees, that could be from 0 to 10, or it could be from 10 to 20. The difference doesn't matter where the 0 is when I do subtraction between 2 points. So essentially, hydrogen has been chosen as the 0 point for the redox table for voltage. And there's reasons for that. The main reason would be that hydrogen is simply, element number 1. It's the most simple atom. So it makes sense that it would be set as 0. It's also in the very middle, which is nice, of our potential voltages. This half cell is a weird one, and it breaks kind of the trend that I said about electrodes having to be a solid, because hydrogen, this half cell would actually be an aqueous hydrogen ion solution, right? So essentially like an acid in here. And then I have a platinum kind of electrode, so an inert electrode that's a part of this half cell. We don't deal with a hydrogen half cell in full cells pretty much ever, but it's a strange one for sure. But again, it is set as 0. So when I talk about a standard reduction potential, as I have in the notes in the bottom here, it's the ability that something has to attract electrons. So as I go up to a higher voltage, that means it is more able to attract electrons. In other words, it's a stronger oxidizing agent. When I have a more low voltage, a more negative voltage, then it's a weaker oxidizing agent. It doesn't have as much of a pull for electrons. There are sometimes questions where it actually gives you voltages and then asks, where would this be on the redox table? And all you have to realize is I'm going from the highest voltage to the lowest voltage. But again, this is the reduction potential. When I'm actually figuring out a voltage for a cell, I'm always subtracting between the two, because when I'm talking about potential difference or voltage, it's right in the name, potential difference, it involves subtracting between two half cells, which you're going to see. So here's an excerpt from the redox table. You can see that I have hydrogen at 0.00. And then if I take a look above that, of course, it's becoming more and more positive, and below it's becoming more and more negative. So what this means is the higher up it is, the more able it is to attract electrons, while the lower it is, the less able it is, the weaker the oxidizing agent. So essentially the reference potential, or the potential that I'm seeing here, I should be saying the standard potential, is its ability to attract electrons. And then if I take a look at a full cell, I'm comparing the two half reactions, the voltages of those, I'm subtracting it, and that actually tells me then what I'm looking at for the full voltage of the cell, which we'll get into for a bit. Now, Alberta Ed is really into the idea of, hey, let's pretend hydrogen wasn't the reference half cell. Let's pretend that I chose something else as the 0. How would that change all the other values on the table? Because again, the choice of hydrogen was somewhat arbitrary. We just chose that as the 0, and then we went from there. So what if we chose something else? What if we chose, for example, this iodine, half cell? How would that change everything else in terms of the voltage values here? So the example I have is, what if the silver half reaction had been chosen? So let's say instead of hydrogen, I chose this instead, okay, silver ion. So this half reaction, which has a value of positive 0.80 volts. So how would that change everything else? So silver, again, is positive 0.80 volts. But now I'm saying that this is going to be the new 0.00 volts. How does everything else on the table shift? So first of all, unfortunately, the table that I have here is not good for seeing this. So let me get to a table that has everything on it, then I'm going to erase it afterwards. All right, so here we go. So I've got silver as 0.80 volts, and now I'm looking at instead bromine. So bromine was positive 1.07. What is it now? Well, essentially all I need to do to figure this out is just subtract positive 0.80 volts from all of these values, because that's now 0. So if I subtract 0.80, and I actually underlined the wrong one here, it's this 0.80. If I subtract that from all the values, then I get the new potentials. So for bromine, it would be positive 1.07 volts minus 0.80 volts. It's also positive. It's important that I put the positives and negatives in there, just like when I did that for energies, endothermic and exothermic. So what I end up with that is I get positive 0.27 volts as a final answer for that. So that would be the new bromine value, positive 0.27 volts. So positive 0.27 volts. Now, what about cobalt? Well, cobalt is right here. I can use this table now. It was negative 0.28. So if I take negative 0.28 volts and then again subtract positive 0.80 volts, I'll end up with my new value, which means that it would be negative 1.08 volts. So the new value for cobalt, it would be negative 1.08 volts. So what I mean by that is what I'm doing on this table is I'm saying, okay, this is no longer 0, but this is now 0. So this is 0.00. And now how does everything else shift? So for cobalt, it would now be a value of negative 1.08 volts. So I'm changing what my reference half cell is. I'm saying that something else is 0. And then the value that it was, I subtract from everything else. So if I were to kind of make up a formula for this, not that it's necessary, if you have understanding, you don't need the formula, but I would just take the new reference, so the new voltage for something would be equal to the previous voltage minus I don't know why that does that, minus the new reference voltage. So in the example I just did, right, I had the voltage of cobalt is equal to the original voltage, so negative 0.28 volts, minus the new reference voltage, so that is positive 0.80 volts, and then I end up with my value. Okay, so one more example. Why don't you take a quick try at this? Okay, so see if you can do this. Now we're making sodium the new reference half cell. Take a look, find the answers, and then come back. And I'm going to pause and get a table in the next cell. And here we go. So I have the sodium half reaction is a new half cell. So sodium is negative 2.71 volts. I like writing it down right away, just so I have this negative 2.71. Oh, the struggle. 1 volts. I did it again. Oh my word. All right. So now if I want iodine, it was positive 0.54. So I have positive 0.54 volts minus, and this is where it gets tricky, two negatives, negative 2.71 volts. So if I go ahead and work that out, I'm going to get positive 3.25 volts. So that'll be the new iodine value, right? And again, what I'm doing is just subtracting the voltage for the new reference half cell, which was negative 2.71. I'm subtracting that from the value that I used to have for whatever I'm looking at, which was iodine. So iodine was positive 0.54, so that's minus negative 2.71, and I get the answer of 3.25. Now, if I were doing this for lithium, going to lithium, that was a value of negative 3.04. So now what I have is negative 3.04 minus negative 2.71 volts. And I end up with an answer for that of negative 0.33 volts. So negative 0.33 volts being my answer for the lithium half cell of what it would be as a value. So that's how you do things when it comes to finding a new reference half cell. It's actually just relatively easy. Whatever the value was on the table, okay, you're subtracting that from other values and you end up with the new value if that was the reference. All right, so now let's get into finding voltages for full cells. So far, we're just looking at half cells, half reactions. So now we're going to look at the standard cell potential for a full electrochemical cell. It's really easy to actually calculate this. All I do to find it is I find the cathode minus the anode voltage, and that gives me the voltage for the cell. If it's positive, this means it's spontaneous, so it's voltaic. So a positive voltage for the cell means that I have a voltaic cell and it's spontaneous. Okay, so that's really important. We're going to, in the future, get into negative voltages, which means that I have an electrolytic cell. In other words, it doesn't actually produce electricity, but it requires electricity in order to function. So let's take a look at a few different cells and try to figure out what the theoretical voltage would be under standard conditions. So first of all, we know right away that this is the anode side and this is the cathode side, because that's always what our cell notation is. Now, if I didn't know that, I could take a look and figure that out a different way. All I would have to do is say, okay, well, I have the aluminum and the nickel half reactions. So I have aluminum right here, and then I have nickel 2 right here. So this is the OA, and this is the RA. So this would be the anode, right, where oxidation happens, and this is the cathode, where reduction happens, the solid nickel. So I have negative 1.66 and negative 0.26. So negative 1.66, negative 0.26. I'm now doubting that my memory is correct on that. It's good. Okay, so now I've got cathode minus anode. So all I need to do to figure out the voltage is negative 0.26 volts minus negative 1.66 volts. So cat minus an. It's going to sound like a really dumb trick, but what I imagine is there's a room with a cat and a girl named Anne. I just want the cat. I don't want the Anne. Get rid of Anne. I just want to pet the cat. So what I've got then is cat minus Anne. Take away Anne, life is rich and full. So if I take a look at example 2, I'm sorry if anyone's named Anne. That would be really mean. You're a wonderful person, Anne. Moving forward, if I look at the aluminum and this hydrogen and nitrate ion cell, again, that I know that this is the anode and this is the cathode. This is very specific in terms of what I have here. So I know that I'm actually going to find this weird reaction, and it's the one that's right up here with the nitrate and the H positive. So that's my cathode. And then I have the same negative 1.66 for my anode. So I've got positive 0.80 for my cathode here, negative 1.66 volts for my anode. So again, I have cat minus N, so positive 0.80 volts minus negative 1.66 volts. So I work that out and I get a voltage equal to positive 2.46 volts. The big trick for this is simply the fact that you have to subtract a negative sometimes. And that means that really you're adding that value, right? Because math that you learned back in elementary, probably. Late elementary, early middle school, who knows? So what is the maximum voltage a cell can have based on your redox table? If you take a look at this table and you try to figure out, all right, what's the craziest cell that I could actually have, what would that be? Well, it would be a fluorine lithium cell. So I would end up with positive 2.87 volts for my cathode minus negative 3.04 volts. And I would end up with a 5.91 volt cell. Now, fluorine cells aren't particularly realistic. But when you look at lithium ion batteries, I forget how crazy they are, but they're somewhere around like 4.20 volts or something like that. And it's most likely actually using this manganese oxide paste, but I'm not sure about that. Obviously, it's using lithium for lithium ion batteries, right? We've got this as my anode, but I forget what the cathode is. It might be an interesting Google search to actually see what that is. But yeah, okay, so maximum voltage I could have is positive 5.91 volts. Add this half reaction to your periodic table for the next worksheet. So this half reaction right here is one that I think gets used in one of your worksheets. So it's just good to have. Keep that in mind. So take a second, write that down somewhere on that redox table sheet. And it's a strong one, right? A positive 1.20 volts. And it's an interesting one, this iodate and then acidic conditions, making iodine and water. So something to write down for sure. And it would fit in just right around here. Yes, 1.20 volts. So right around there between bromine and the manganese oxide paste reaction. Now, obviously, you can't fit it into this small little spot, but maybe just write it on the side here or something of your table, and then draw yourself a little arrow to know, hey, it's fitting in right there. Okay, let's try one more of these out. And in fact, I think that this is a good situation where you could pause it and then come back and see if you got the right answer. So pause, try out this question, and then come back and let's see how you did. All right, so let's try this out. Copper and zinc voltaic cell. So going back to my table, I really should clear off some of this ink. I have copper, I have zinc, so zinc is going to be my anode, copper is going to be my cathode. So I have positive 0.34 and negative 0.76. So positive 0.34, negative 0.76 volts. So I have the voltage of the cell being cat minus N, so positive 0.34 volts minus negative 0.76 volts. So I end up with an answer of positive 1.10 volts. So that would be the voltage for, again, what we call Daniel's cell, copper and zinc together. If the bromine half reaction was a new reference half cell, 0.00 volts, what would be the voltage for the copper zinc voltaic cell? Now, it's the same difference because differences are the same despite whatever reference we have, but let's prove it. So this is now 0.00 volts for bromine. So I'm subtracting positive 1.07 from both of these. So minus positive 1.07 volts for this. And I'm going to minus 1.07 volts from this. So I end up with an answer of, math is hard, negative 0.73 volts. And here I have negative 2.83 volts after that. So this is now what I have in terms of my new voltages. So now again, I do cat minus N. So I have negative, wrong way, negative 0.73 volts minus negative, what was the value? 2.83 volts. And hooray, it works out to be the same value of positive 1.10 volts. So it doesn't matter what our choice of the reference is, the difference between two half cells will always be the same, right? If you got 10 bucks, it doesn't matter if your account was at $20 to begin with or $2,400 to begin with, you still got 10 bucks. It's still the same difference, right? So what I'm looking at is a difference between 2 points. It doesn't matter what the zero is, the difference will remain the same. Does the choice of a reference half cell change the voltage for a full cell? The answer to that is a big no. And the diploma loves this, loves it, loves the reference half cell, and then loves asking you for a difference afterwards. All right, so last thing we're going to talk about before we end for today is why do batteries die? Well, batteries can die for a number of reasons. For example, it might run out of reactant, right? So one of the reactants, the OA or the RA, ends up just kind of running out. So we no longer actually have anything available. You could have side reactions that occur that are not intended, right? But this is like rechargeable batteries, for example. You don't get maybe the full anode back as it's recharging. You don't get as much there. So you're running out of reactant. And the reason why you're running out of reactant is because there's side reactions that happen or that anode just can't be rebuilt. But the big thing is that we run out of reactions or chemicals just mix so much through the porous boundary that it no longer can function because OA and RA have now mixed, so it no longer has to actually go through the wire. Okay, now one thing to mention is that when we actually look at real cells, the voltages don't always come out to the values that we predict from the table. And in fact, your table is built to be 25 degrees Celsius, and I forget if it's 1 mole per liter or 0.1 mole per liter for concentrations, but it's ideal conditions. It's just a guide of what the voltage could be, but you could get higher or lower depending on how you build the cell and different factors. So why does it end up being possibly different, the voltage you get in reality compared to theoretically on paper? Well, because you could have differences in temperature. In fact, you guys probably know that temperature is a huge factor for batteries. If you have things that are really cold, the battery does not work very well. Hence car batteries, right? Needing to be heated up in order to start your car when it's incredibly cold conditions. I remember walking to school back when I was in high school, early high school, and I had a Walkman. I was behind the times. I didn't have a CD player yet. So I had a Walkman and I was playing tape cassettes. And it was funny because walking through the cold, the voice would actually get deeper and deeper and deeper of the singing, right? Because of the fact that it was slowing down how fast the tape turned as the battery was putting out less and less current or voltage. And that was because of the temperature going down. So temperature is a big factor. The voltages that you calculate is based on SATP conditions, 25 degrees Celsius. If you have gases involved, pressure can be a factor. Purity of substances, a big factor, like concentration or how pure something is. Presence of oxide coating, meaning that the cathode or anode isn't available because of the fact that there's some kind of impurity on the outside or an oxide coating that's stopping the reaction from happening at its surface. And then the porous boundary is a big factor as well, the type and size and the amount of movement it allows, the amount of mixing it allows, that's also a factor. So what are you supposed to get out of this? The main idea is that things do not always work out as you expect for voltages, and these are some of the reasons why that can happen. Normally, you would do a lab at this point where you build a battery out of a pop can, and I just give you a list of materials and you kind of go at it and see what you can build. And then we do actually a competition to see who builds the best battery that puts out the highest voltage and highest current for the highest power for the battery. It's always really interesting, but normally students get values that are much higher than they normally would be able to get based on the table. And that's because they improve some of the factors. So they maybe heat up the solutions, or they remove all the oxide coating on the metals to make sure it's very, very pure, or they have a higher concentration of reactants and it works better than than you would expect based on the values on the table. Okay, so I believe that is it. Yep, we're on to electrolytic. So yeah, electrolytic is the next lesson, but that's it for voltages for today. Have a great rest of your day.